When we think about the search for life beyond Earth, most of us imagine distant planets in far-off galaxies. But one of the most promising places to look isn't light years away. It's right here in our own solar system. It's a frozen world called Europa, one of Jupiter's largest moons. At first glance, Europa seems cold, quiet, and lifeless. But beneath that icy crust lies something extraordinary, a deep global ocean that could be teeming with alien life. Could this distant moon harbor the conditions for life? And if so, what kind of life might we find? In this video, we dive into the science and the tantalizing clues that suggest Europa may be one of the most promising places to find life beyond Earth. Europa is the fourth largest among Jupiter's 95 known moons. It is just a bit smaller than our own moon, measuring about 3,100 kilometers, or roughly 1,940 miles, in diameter. That puts it firmly in the category of small but significant, especially when we consider the mysteries beneath its icy crust. Europa completes a full orbit around Jupiter in just about 3.5 days. Like many moons in our solar system, it's tidally locked to its planet. That means one hemisphere constantly faces Jupiter, while the other remains turned away. Because of its great distance from the Sun and its lack of significant atmosphere, Europa's surface remains bitterly cold, averaging around minus 160 degrees Celsius, or minus 260 degrees Fahrenheit. That might seem inhospitable, but as we'll see, Europa has layers, literally and figuratively, that make it one of the most exciting destinations in the search for extraterrestrial life. The first thing that stands out about Europa's surface is how extraordinarily smooth it is, almost eerily so. There are no towering mountains, sprawling canyons, or massive impact basins like we see on Earth, Mars, or even our moon. Instead, Europa's exterior appears like a sheet of cracked glass stretched tightly over a hidden ocean, with only modest elevation changes across its entire landscape. In fact, if you scaled Europa down to the size of a billiard ball, it would be smoother than the ball itself. The surface is made almost entirely of water ice, likely extending several kilometers deep. But this shell isn't static. It shows signs of dynamic processes at work, processes that mimic plate tectonics on Earth, but with key differences. The fractured crust is laced with ridges, bands, and chaotic regions that seem to have been torn, rotated, and resealed, suggesting that Europa's ice is not a solid inert block. Instead, it's flexible, mobile, and geologically active. The most prominent features are the long linear cracks and ridges that stretch across hundreds, sometimes thousands of kilometers. Many of these are double ridges, paired lines with a trough in the middle. These may form when the ice crust is pulled apart by tidal forces from Jupiter's gravity. As the crust separates, warmer ice or slushy material from below could well up, refreezing in the gap and forming the raised ridges seen today. This is a recurring process. Some ridges even have repeating patterns, indicating cyclic deformation over time. Even more puzzling are the so-called chaos terrains, disordered regions where the surface appears to have been shattered, moved, and reassembled like broken plates of sea ice. These zones are defined by irregular blocks of ice that seem to have floated and rotated before settling into new positions. Some scientists believe these terrains form when localized heating from below causes the ice shell to partially melt or weaken, destabilizing the area. In effect, it's as if the icy crust locally collapses and reforms, a process far more dynamic than we'd expect from a small, frozen moon. And again, what powers this activity is not the Sun, but Jupiter's immense gravitational pull. The tidal forces flex Europa's interior on every orbit, generating heat and driving internal movement, even in the absence of volcanic rock or significant solar input. Perhaps one of the most compelling pieces of geological evidence comes from what's missing: impact craters. Unlike our Moon, Mars, or Mercury, Europa has very few visible craters. This tells scientists two critical things. First, the surface is relatively young in geological terms, likely no older than 40 to 90 million years, and possibly much younger in some regions. Second, something must be actively resurfacing Europa and erasing the scars left by meteor impacts. On airless worlds, craters accumulate over billions of years, but on Europa, they get buried, filled, or restructured, likely by movement in the ice shell or by material upwelling from the subsurface. In effect, Europa's surface is constantly being rewritten, suggesting a dynamic interaction between the crust and what lies beneath it. That brings us to a mystery that's visible even from afar: the color of Europa's surface. When the Galileo spacecraft sent back high-resolution images in the 1990s, scientists were struck by the reddish-brown streaks crisscrossing the moon. These hues stand in stark contrast to the surrounding ice and raise critical questions about composition, source, and mechanism. One of the leading theories is that these colors are caused by salts, particularly magnesium sulfate or sodium chloride, substances we associate with Epsom salt or table salt here on Earth. These salts may originate from the subsurface ocean, brought up through the cracks or chaos terrains by internal pressure or tidal flexing. Once on the surface, they become exposed to the harsh environment of space, intense radiation from Jupiter's magnetic field, bombardment by energetic particles, and exposure to extreme cold. This process, known as radiolysis, breaks down the molecules and alters their chemical structure, producing the darker, reddish hues seen from orbit. But it's not just salt at play. There's evidence that sulfur compounds may also be involved, possibly originating from Io, Europa's neighboring moon, which is the most volcanically active body in the solar system. Io spews sulfur into space, and some of that material could make its way to Europa, either settling onto the surface or interacting chemically with the existing ice and salts. Europa's crust is cold and brittle at the surface, but as you go deeper, the increasing pressure and residual heat make the ice softer, even ductile. Estimates for the thickness of this ice shell vary, but most models suggest it ranges between 15 to 25 kilometers. Some parts could be thinner, especially near the chaos terrains, where the surface appears to have been disrupted from below. Beneath Europa's fractured frozen shell lies what may be one of the most expansive oceans in the entire solar system. The layered structure of the moon points clearly to a liquid water ocean trapped between an icy crust and a rocky interior. But this isn't just an isolated pool, it's a vast, global ocean, and its scale, composition, and energy dynamics place Europa at the center of modern astrobiological research. While the structure tells us that an ocean likely exists, it's the water itself, its volume, chemistry, and potential for sustaining life that makes Europa so compelling. Let's begin with the scale. Europa may contain more water than all of Earth's oceans combined. That might sound surprising given its smaller size, but the numbers are clear. Earth's oceans hold about 1.4 billion cubic kilometers of water. Estimates for Europa's ocean volume fall around 2 to 3 billion cubic kilometers, depending on the exact thickness of the ice shell and the depth of the ocean beneath it. The ocean is possibly 60 to 150 kilometers deep. This is astonishing, considering Earth's average ocean depth is only about 3.7 kilometers. This enormous volume of water isn't locked in surface ice. It's thought to be fully liquid, kept warm by tidal flexing generated by Jupiter's gravitational pull. That heating mechanism continuously works Europa's interior, keeping its water from freezing solid despite the extreme cold of the surface. Unlike Earth, where sunlight drives the surface energy balance and regulates the water cycle, Europa's heat source comes from below, making the ocean an isolated, yet potentially stable environment over geological timescales. But what kind of ocean is it? If it were just pure water, cold and inert, the chances of finding life might be slim. Life, at least as we understand it, needs more than water. It needs chemistry. Fortunately, there are reasons to believe Europa's ocean is chemically rich, and possibly even oxygenated. Surface spectroscopy has shown that Europa's icy crust contains salts, particularly magnesium sulfate, and possibly sodium chloride, the latter being chemically identical to common table salt. Since these salts are concentrated along cracks, ridges, and in the chaos terrains, it's likely they originated in the subsurface ocean and were transported upward during periods of geologic activity. But their very presence implies that Europa's ocean is not just liquid, but saline. A salty ocean is significant. Salt increases the electrical conductivity of water, supporting the magnetic induction evidence that Galileo recorded. It also provides ions essential for many biological processes. On Earth, life thrives in saline environments, from the deep ocean to salt lakes. If Europa's ocean contains similar chemical building blocks, it strengthens the case for habitability. In addition to salts, Europa may also host oxygen. This is not molecular oxygen floating freely in the ocean, but rather oxidants produced on the surface ice through radiation processing. Energetic particles from Jupiter break apart water molecules, creating reactive oxygen species. These oxidants may then migrate downward through cracks or convection in the ice, eventually mixing with the subsurface ocean. If this transport is efficient, and recent models suggest it might be, then Europa's ocean could have a surprisingly rich chemical profile, oxidants from the surface mixing with reductants from interactions with the rocky seafloor. That redox chemistry is the exact kind of energy source that life on Earth exploits. And this brings us to the possibility of hydrothermal activity. On Earth, deep-sea hydrothermal vents lie along tectonic boundaries, where seawater interacts with magma-heated rock. The resulting chemical reactions release hydrogen, methane, and a range of metal ions, creating energy-rich environments that support entire ecosystems. Without sunlight, life in these extreme zones includes tube worms, clams, and a host of microbial species that rely on chemosynthesis rather than photosynthesis. The organisms derive energy from chemical gradients rather than solar energy, which makes them a perfect analog for what might exist beneath Europa's ice. Could Europa have its own version of these hydrothermal vents? It's a real possibility. The Moon's interior likely contains a rocky mantle, and that mantle may be in contact with the ocean above. If Europa's core retains residual heat, or if tidal flexing continues to warm the mantle, then liquid water could seep into the porous rock, leaching minerals and generating chemical energy. This is the same mechanism that drives hydrothermal vent activity on Earth. In fact, modeling suggests that Europa may have more hydrothermal activity per kilogram of rock than Earth does, thanks again to the tidal heating from Jupiter. There's even evidence, albeit indirect, that vent-like activity may be happening. For example, certain chaos terrains resemble regions on Earth where the seafloor has been disrupted by upwelling thermal activity. Moreover, if Europa's ocean floor is geologically active, it could provide a steady source of chemical energy and nutrients, essential ingredients for maintaining any ecosystem over time. And since the ocean is likely tens of kilometers deep, it provides a massive volume in which such systems could exist and evolve. It's important to emphasize that none of this guarantees life exists there, but the conditions, liquid water, essential elements, chemical gradients, a long-lived heat source, are consistent with the basic requirements for life as we understand it. Europa may not have sunlight or a breathable atmosphere, but neither do Earth's hydrothermal vents, yet they teem with complex, thriving ecosystems. It's plausible then that if life ever took root in Europa's ocean, it could still persist today, hidden beneath the ice, feeding on chemical energy, and possibly evolving into forms radically different from anything on Earth. Everything we've covered so far builds toward this possibility, but what kind of life could actually survive there, and just how realistic is that hope? If life can exist at the bottom of Earth's oceans, it may well survive in Europa's. Any potential Europan life would likely be microbial, simple single-celled organisms capable of metabolizing chemical energy from the surrounding environment. This doesn't mean Europa is crawling with life, but if the conditions are right, liquid water, a source of energy, and the right chemical ingredients, then microbial ecosystems could persist for millions, even billions of years. What would such life need? The basic requirements, as understood by biologists, include a solvent, water, a stable energy source, chemical or solar, a source of carbon, and key elements like hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Water is almost certainly present. Chemical energy could be derived from hydrothermal activity or surface-derived oxidants. Carbon could come from organic molecules synthesized through abiotic chemistry, delivered by comets, or even produced via serpentinization reactions in the rocky mantle. Nitrogen, phosphorus, and sulfur could be present in trace amounts, as they are on Earth. In short, the essential ingredients are plausible, if not yet confirmed. But plausibility is not proof, and the scientific community remains divided, not on whether life could exist, but whether it does. On the pro side, the most compelling point is water, specifically stable, long-term liquid water in contact with rock. Every environment on Earth that has water, even the most extreme, seems to support life. In fact, we have yet to discover a truly sterile body of water on our planet. Add to that the evidence for chemical energy from hydrothermal activity and the potential delivery of surface oxidants into the ocean, and you have a system that appears capable of supporting metabolic processes. Furthermore, if organics are present, either generated internally or delivered by comets or meteors, they could provide the carbon backbone for biological molecules like amino acids and nucleotides. Another argument for life is based on duration. Europa's ocean is not a transient or recent phenomenon. It has likely existed for billions of years, potentially for most of the history of the solar system. That's a significant stretch of time, and if life ever did emerge, it would have had ample opportunity to evolve, adapt, and possibly diversify. On Earth, microbial life arose quickly after conditions stabilized, which suggests that when the right elements come together, biology can ignite rapidly. If that's a universal pattern rather than an Earth-specific fluke, then Europa becomes a prime candidate. But there are arguments against this optimism, and they're worth taking seriously. First and foremost is radiation. Europa sits deep within Jupiter's magnetosphere, which traps and accelerates charged particles, bombarding the Moon's surface with intense radiation. This radiation sterilizes the upper layers of the ice, breaking down organic molecules and making it difficult for life to persist on or near the surface. However, since the hypothesized ocean lies tens of kilometers below, it would be well shielded from this radiation. The real concern isn't that life couldn't survive underground, it's that the surface is inhospitable to any biosignatures that might escape or be deposited there. Another challenge is the absence of sunlight. While life on Earth's surface depends on photosynthesis, Europa's ocean is shrouded in perpetual darkness. This doesn't rule out life. Deep-sea organisms on Earth live without sunlight, but it does limit the kinds of ecosystems that could exist. Without light-driven primary production, any food web on Europa would have to rely entirely on chemosynthesis. That places constraints on the complexity and energy budget of any ecosystem that could evolve. There's also the issue of the ice shell. As we've already discussed, estimates place it anywhere from 15 to 25 kilometers thick, though thinner in certain active zones. That's a substantial barrier between the ocean and the surface. If life exists in the ocean, how could we detect it without direct access? Surface materials may not preserve biological markers for long, especially under constant radiation exposure. Even if Europa does have plumes ejecting ocean water into space, those plumes are likely intermittent and weak, making them difficult to sample with current technology. Without direct access to the ocean or reliable access to surface-expressed material, proving the existence of life becomes a technological challenge as much as a scientific one. Finally, we must acknowledge the possibility that Europa's ocean, while physically suitable, may simply lack the critical chemical conditions needed for life to originate. Life is not just water plus molecules. It's a specific, self-organizing chemistry that may require finely tuned conditions or rare events. Just because Europa looks habitable doesn't guarantee it is inhabited. Still, the balance of evidence supports the idea that Europa is at least a potentially habitable environment. It checks many of the boxes: liquid water, chemical gradients, essential elements, geological activity, and does so on a global scale. Even if life is absent, the ocean itself would be a major discovery, a vast alien sea operating under a different set of physical and chemical rules than anything we see on Earth's surface. The question of life on Europa remains unanswered, but we are inching closer. The next chapter begins with Europa Clipper, NASA's flagship mission to Europa. which launched in 2024 and is now en route to the Jovian system. Europa Clipper is designed not to orbit the moon directly, but to perform multiple close flybys, around 50 in total, as it orbits Jupiter. This approach avoids the intense radiation belts around Europa, while still allowing for detailed, repeated observations. Each flyby will target different regions of the surface and collect complementary datasets, helping build a comprehensive picture of Europa's structure and chemistry. The mission's scientific goals are tightly focused. First, it aims to determine the thickness of the ice shell and the depth and salinity of the ocean beneath. Second, it will assess the composition of the surface and subsurface, including the potential presence of organic compounds. Third, it will search for signs of recent or ongoing geological activity, like plumes, active cracks, or fresh chaos terrains. Fourth, it will characterize the surface for potential future landing sites. To accomplish this, Europa Clipper is equipped with a sophisticated payload. Its radar system will penetrate the ice to estimate thickness and detect layering. Its magnetometer will refine our understanding of the induced magnetic field and, by extension, the ocean beneath. A thermal imaging camera will look for hotspots, potential indicators of recent surface activity. A suite of spectrometers will analyze surface composition, searching for salts, organics, and oxidants. There's also a high-resolution camera system designed to map the surface in unprecedented detail. And if Europa is releasing water vapor plumes into space, as Hubble observations tentatively suggest, Europa Clipper will have instruments to fly through them and analyze the material directly. With upcoming missions like Europa Clipper, we're getting closer to finding out whether this hidden world is just habitable or truly inhabited. The answers could change how we see life in the universe. If you enjoyed learning about Europa, please like the video, subscribe, and press the notification bell for more stories about our universe. Thanks for watching, and see you next time.